Yeah, a very good day to all. So in the previous sessions, we have discussed about the sequential introduction about the sequential circuit, and as well as about the set reset flip flop and the JK flip flop. Now the third type of flip flop under our study is called as your D flip flop. The D flip flop is also called as your data flip flop. And why this D flip flop has been designed is, we know that this D flip-flop is a modified version of your SR flip-flop. Say it can be also an JK flip-flop too. Okay. So in an SR flip-flop, a condition that may prevail is called as your race around condition. When both your set and reset inputs are equal to 1 and 1, then the flip-flop will be moved into a state called as your indeterminate state. So here, this D flip-flop is an alternative form of SR flip-flop which removes the condition of your race around. Okay, so the logic diagram will be like this. Uh, you will be taking an SR flip-flop. In this, the input D is directly fed to S. Okay, but whereas it is given through an inverter, that the D input is directly given through an inverter and it will be fed to a R. This logic diagram is an equivalent model of converting an SNR flip-flop or a JNK flip-flop into a D flip-flop. Conversion of an SNR flip-flop or a JNK flip-flop into an D flip-flop. The truth table of this is, so truth table is when your input is equal to 0, okay, your current input is equal to 0, your Qn plus 1 is equal to 0. When your input is equal to 1, your Qn plus 1 is equal to 1. So whatsoever your data is given, that completely fed as your output. So only the other name of data flip-flop is there for this D flip-flop. And this is the complete diagram. This is a conversion diagram, and this is the complete diagram of an D flip-flop which will be having only one input. Okay, and this is your clock signal. If a bubble is there in front of a clock, means then this type of clock is called as your negative edge triggered clock. If you don't have the bubble, just a line is there, then we can say that it's a positive edge triggered clock. Okay, so the clock is an clock driven devices are called as your edge triggering devices. Edge triggering can be of two types. One is called as your positive edge triggering and next one is called as your negative edge triggering. In a curve, for example, say you are having a square waveform, means, okay, square waveform starting is called as your positive edge triggering. Okay, square waveform ending is called as your negative edge triggering. So your positive it's triggered or negative it's triggered. So here it is triggered with the help of an negative edge triggering. Q and Q bar are your output and it's complementary, and the preset and clear are the two other inputs which is used to clear the previous ASCII values that may get previous ASCII values or redundant values that have got stored in the flip flop. Okay, now we are into the findings of your characteristic table, the state diagram, and as well as the excitation table. So the name or the symbol is, it will be having an input and the clock signal Q and Q bar is your output. Okay, so now the characteristic table or the truth table is, we know that your D, okay, your data input is your 0 and 1, your Q next, that is called as your Qn plus 1. Whatsoever, irrespective of the value of your Q, irrespective of the current state output, your output, the next state output is equal to the same as to that of your D input. So your D input is your 0 and 1, means your next state output will be the same D. Your Q value won't have any impact on the Q next. Okay, whatever is getting given as input, that will get published as your Qn plus 1. And for your excitation table, so your Q and Q next are the two inputs, right? Q and Q next are the two inputs and your D is your derived output. So you are having two inputs, means you can write your input combinations as 0 0 0 1 1 0 and 1 1. What I have told is, see, when your Q, when you write your truth table, when you write your truth table, whatever has been published in D will get published in Q next. And here also the same, the inverse. Okay, whatever is present in your Q next is your output at your D. So your 0 1 0 1, and this is called as your state diagram. In the state diagram, what you can do is, your Q is equal to 0 and Q is equal to 1. Okay, when your D is equal to 0, it can be written, and when your D is equal to 1, it is written in 1. When D is changing from your 0 to 1, It will change this when your D is changing from your 1 to 0. It will change to this Q output, Q naught. So when you want to give an output expression for your characteristic equation, how to draw is, so this is an two variable K map could be used, and when you plot for your Q next is equal to 1, when you plot for Q next, it's equal to your D. Your Q next is equal to D is your characteristic equation. See, says that this D flip-flop is generally used for the state diagram minimization and state minimization, because since it is having only one input, and the excitation table and the characteristic table and the characteristic equation, everything is in point blankly direct equations. This is preferably used in the state diagram minimizations, unlike other flip-flop JK, SR. Okay, D flip-flop is preferably used. And thanks for watching. The next topic will be your T flip-flop.